All right, guys, welcome back to another lesson. Just to make sure that that you're in class, in the school. But today is hat day. Okay, I had multiple hats. I had my CSI hat on today. Gotta love the hair. I had my Viking hat on today. I had a hat for every period today. So just so you can see what was going on, I had that. Let's see. I also had a little biker cap on. All right, trying to look cool. And then currently, for this period, which is my planning period, but I have the like the jazzy looking hat on today. So, why not? I thought it was kind of fun to have a hat day, but I'm wearing one for each period. Today's lesson, I don't like using the word lecture, but is on systems of equations in three variables, okay? And I don't have to worry about graphing this time. We've been graphing for so long, now you don't have to worry about it, okay? But we are going to incorporate one little graph, just one. Let's talk about one. Let me come up with the example here. Okay, here's the first thing we're going to look at visually. As a review, if I had an equation that looked like this, okay, and if I were to graph that, I know that's going to be a line, right? And a nice xy plane, I'm graphing a line. But when I add another variable to this, a z variable, what is it going to look like? Okay, well, I'll tell you one thing. This is going to be graphed in an xyz plane, okay, z being like the height. So I'm graphing the 3D area, but still, what is this guy? Is it another line in 3D space, or is it something different? So what I encourage you to do right now is pause the video. Okay, in fact, let me just zoom this in. Oh, you're coming. There you go. Coming towards the screen. So I want you to come up with solutions for this guy. So what can I plug in for x, y, and z that gives me 6? So pause the video and do that. I'm going to go ahead and start writing answers. I can make this guy a 3. I can make this guy a -2 and z to be 6. That's one solution for this guy. So 2 times 3 is 6. Plus 3 times -2 is -6. They cancel out. 6 goes into here. 6 equals 6. It works. Okay. And the point, this is the x-coordinate, the y-coordinate, the z-coordinate. So there's one solution. Okay. Another solution, I can make this guy a 3 and then the other guy zeros. That gives me 6. I can make the first one a 0, the second one a 2, and the last one a 0. I could make the first 2 zeros and the last answer a 6. Now, as I continue, I can keep listing more and more points. There's an infinite number of points here that I can list for solutions. So when I graph all these points, okay, when I'm graphing this, what am I seeing here? Well, I'm not looking at a line anymore, right? I'm actually looking at a plane. All of these solutions are going to be mapped out on a plane. Remember from geometry what planes are? Okay, 3 non-collinear points make up a plane. So this area are all the solutions that I have for this guy. Does that make sense? So it's not a line, it's actually a plane. Now, let's think about this a little bit differently. What would happen, let me erase this. Let's add this to the mix. If I add 2 more equations with 3 unknowns, now I have 3 planes in this picture. Okay, I could have a plane going behind this plane here. Actually, I'll put dots so you can see it goes behind the plane. Okay, I could have another plane coming out diagonally. Okay, like this. So the goal is, and let me just show you, if I want to find an answer to this system, it's like if I'm taking 3 pieces of paper, okay, and what I'm trying to do, I don't know if I can be able to balance this, So like here's two planes intersecting, which would be a line, would be all my solutions. But now if I have a third plane, okay, so here's this one, here's this guy, and here's another plane I'll put on top here. Now I'm trying to find where all three planes intersect. And they all intersect at a point. So there's one point in here where all three planes are laying, okay? And that's what we're looking for. So the answer to a system of three equations with three unknowns is a point, okay? A point in the 3D space here where all three of these planes intersect. Now let's think about what we discussed with two equations with two unknowns. We were trying to find the solution where the two lines intersect, right? If there was no solution for that, if you remember, when we talked about like this, okay, when you had a system like this, that was parallel lines, right? That indicated no solution. So in 3D space, no solution would be what? Parallel planes, okay, two planes that never intersect, or three planes that never intersect. That'd be no solutions, okay? The other way to look at it, maybe these two planes intersect, and let's say these two planes intersect. So it could look like this, okay? Here's, and I'm not going to draw 3D, I'm kind of bad at that, but let's say this is one plane, this is another plane, this is my third plane. They all intersect, but not at the same point. That's another no solution region, okay? Now let's think about the last case, infinite number of solutions. Well, when we talked about a system like this, remember when they were the same line? It was the same equation, so that means you only have one line being drawn, so that was infinite number of solutions, right? Well, let's think about planes. What if I have two or all three of them actually be the same equation? That means I'm only drawing one plane, which means there's infinite number of answers for that one plane. Okay, so a little intro as to what to see geometrically for this, and hopefully that helps. So that way when you're going through a lot of this algebra, you can kind of see visually, oh, that's where all three planes intersect. Or, oh, wait a minute, the planes must be parallel, so there is no solutions. Okay, so I really do think that's important. All right, this would be part one. All right, I'm going to do this in possibly three parts. In part one, we're going to do two examples together. All right, in part two, we're going to talk about the no solution, infinite solution case. And then in part three, we're going to do some word problems. All right, so let's go ahead and look at the first example. Maybe, if I figure out where my papers are. Oh, there they are. Sorry about this. So let's talk about our very first example. And let me just, there we go. So example one. Here's my system. All right, and I want to figure out where all three of these planes intersect at. Is there a point that they intersect? So in other words, I got to figure out what an x, y, and z coordinate that's going to make all three of these guys true. There's a little bit of a glare. Let me just, hopefully that helps a little bit. Okay. Now, I could graph this, but once again, it's 3D graphing. That's going to take a long time, and that's going to be very tedious, not very time efficient. We're going to solve this using elimination and substitution. We're going to use a combination of both, okay? And here's how we're going to do it. I'm going to mark down that the top one is equation 1, this one's equation 2, and this guy's equation 3. And the reason why I'm marking those is so I can use that as a quick reference, all right? Because we're going to be writing a bunch of work here. I'm going to pick two equations to work with at a time, and I want to eliminate one of the variables. Now, you have a choice as to which one you want. So, for instance, look at equation 2 and 3. If I multiply the equation 2 by 2 and add it to equation 3, you see how the z's would cancel out? So that's getting us closer to knowing one of the variables. So that's what I'm going to do. So over here, I'm going to explain that. Okay. In fact, I'm going to use a different color. There we go. So what I'm going to do is multiply equation 2 by 2 and then I'm going to add it to equation 3. I'm going to write myself little notes as to how I got each set of equations. All right, so let's do that. So this guy I'm going to multiply by 2. So I get 4x plus 2y minus 2z equals 10. And then down here, x plus 4y plus 2z equals 16. I did nothing with that third equation. Okay? All right. So now I'm going to add these equations to eliminate z. Okay? So 4x and an x gives me 5. 2y, 4y gives me 6y. The z's cancel out. And then 10 plus 16 gives me 26. Okay, so now I have a smaller equation. It has 2 variables, but I'm not close to what x and y are yet. So what I'm going to do is I'm going to go back to this guy, and I want to come up with another equation that has only x and y in it. Okay? All right, so we did 2 and 3. So let's do 1 and 2. And here's the cool part. I'm actually going to do the same thing. If I multiply this by 2, and if I add it to equation 1, you see how the z's cancel out there as well? I think that would be perfect. So let's do that. So I'm going to multiply equation 2 by 2, and then add it to equation 1. Okay? So let's do that. So this would be another 4x plus 2y minus 2z equals 10. And up here, I got 5x plus 3y plus 2z equals 2. And I'm going to add those guys together so I can eliminate the variable z, just like what I did over here. So add those, I get 9x. This gives me 5y. The z's cancel, and I get 12 on this side. Rating. So far, so good? Now, here's the deal. Okay, this way that I went is actually going to show a lot more work, and that happens. Okay, what I did in the morning class, I did something different. So I could have did a different combination if I wanted to. But here's the deal: you don't want to do equation 2 and 3 and then do another equation 2 and 3 differently. You're only looking at 2 equations here. You're not looking at all 3. So you should be using a different combination when trying to eliminate one of your variables. Okay, so I got 9x and a 5y, 5x and a 6y. Wow, I really made this tough on me. So what variable do I want to get rid of, x or y? Well, I'm thinking y would be nice. So what I'm going to do, okay, is I'm going to multiply, and I'm going to make this equation 4, and this is equation 5. Once again, I am labeling it to make it easy to reference. So I'm going to multiply equation 4 by a negative 6, and then multiply equation 5 by a 5. Then I'm going to add them. Okay? I'm going to try and eliminate y. Now you could eliminate x by doing the same thing. Multiply this by like a negative 5 and this one by a 9. Okay? Either way, that can help you with it. Okay? So now over here, I'm going to write that work. So, we're going to have, that's going to be some higher numbers, but that's okay. We'll still work with it. Not all the time will you have to multiply both equations here. So for this guy, that's going to be a negative 54x minus 30y, okay, equals, that'll be what, a negative 72? And then for this guy, I'm going to multiply it by 5, so I get 25x plus 30y equals, what would that be? So 310, 130 for that guy. And once again, I'm going to add those two together. Hopefully you can see like the importance of labeling all of this because it can get a little bit tedious. So, adding these guys together, okay? So if I add the first one, just want to make sure I'm going to, because here's the deal. I don't want to do this and be incorrect. So I'm going to cheat a little bit with the calculator. So we get negative 29x. The y's cancel, okay? And that's going to equal, what, a negative, or no, not a negative, a positive 58 for that guy. I did it. I achieved my goal. I actually have one variable left that I could solve for. So I'm going to divide both sides by negative 29, and I get x to be a negative 2. I finally have one of my variables, okay? I know, that's a lot of work, but here's the good part. To figure out the other variables, I'm going to use substitution method. So now I'm going to substitute this guy back into one of my other equations and solve for y. The question is, which one do I try? Well, I don't want to plug this into this original because then I have two unknowns. That's not going to work. So I'm going to plug this guy either into equation 4 or equation 5 and solve for y. And I want to pick probably the easiest one. I don't think it really matters. I mean, looking at what I have left, so I don't know, we can plug it into this one, okay? So here I'm going to say I'm going to sub into equation 5, okay? Now, I'm going to scroll the screen. There we go, because I'm running out of space. So I'm going to plug it into here. So 5x plus 6y equals 26. So let's go ahead and substitute. Okay. So let's see. This is going to be a negative 10, which if I add it to the other side, I get 36. And if I divide, I get y to be 6. Okay. Now, here's the deal. Now I know what x and y are. I got to figure out what z is. So what I'm going to do, let me just come back. So now I'm going to take both of these guys and substitute it in one of the original equations to figure out what z is, to finalize it. So it doesn't really matter. I'm going to sub x and y into, we'll say equation 2. Okay, we'll do that. And let me just... There we go, so you guys can see. So equation 2 is 2x plus y minus z equals 5. So let me go ahead and substitute. 2 times negative 2 plus 6 minus z equals 5. That becomes negative 12 plus 6 is negative 6. Add to the other side, right? Am I correct in that assumption? Oh my gosh, no. 2 times, I don't know why I thought that was a 6, sorry. 2 times negative 2 is negative 4, plus 6 is positive 2, subtract it, I get negative z equals 3, and then divide by the negative, z becomes 3. Awesome. Okay, let me just scroll the board a little bit. So let me just go ahead and finalize the answer. So it's negative 2, 6, and 3. That's going to work for all three of these equations, okay? And I'm going to put some context here. So this is the intersection point for all three planes, just like that, okay? So visually, that's all three of those like pieces of paper that all intersect at one point specific. On Google Classroom, I do have for you a reference sheet that shows visually what that looks like better than me just holding up pieces of paper or trying to draw it. So you can take a look at that more visually there. Okay? All right, one problem done. You see why I try to keep it nice and neat and try to label these so it makes it a lot easier for you to, not to follow, but even for you. I mean, if you're doing this, I don't want to have like a bunch of scribbly work everywhere. Then it's going to be hard to figure out where your error went. Okay? So as you can see, if you make an error at the beginning, it's going to affect you at the end. And that's a lot of work to get through. So take your time. Okay? All right, we're going to do one more example, and I'm going to end the video, and that'll be it for part 1. Okay? All right. Oh, this just hurts. I got to erase all this work. All gone. All finished. It does hurt a little bit if you think about it. It's like, man, I put all that work and effort into it. I'm erasing it. Okay. Next example. And then we'll stop. Here it is. Okay. So So let's see, 2x plus 3y minus 3z equals 16. X plus y plus z equals negative 3. X minus 2y minus z equals negative 1. There we go. All right. So we got to pick two equations, and one of them we might have to multiply, but we want to get rid of a variable, and it's your choice what you want to get rid of. I don't think we have to search too far. I don't know if you can see it, but if I add these two equations, you see how z could cancel out? So let's try that out, okay? So I'm going to add equation 2 and equation 3 together. That's my first step. I'm going to rewrite it on this side. Okay. And just a note, you don't have to eliminate z first. I could eliminate x or anything else that I wanted to. I just figured this is a little bit easier because it's already kind of set up for us. Okay. All right, so these x's give me a 2x. Y minus 2y is negative y. The z's are going to cancel, and then I have equals negative 4. I have one equation with two variables. Let's see if I can't get another equation with two variables. So we need to eliminate z again. And, well, I don't know. How about let's multiply this equation by negative 3 and add to this guy. Or actually, I'm sorry. Let's multiply this by positive 3 and add to this guy. That'll get rid of the z's. So I'm going to write down that step. Multiply equation 2 by 3. And then we're going to add it to equation 1. Okay? So here we go. So for this guy, I get 3x plus 3y plus 3z equals negative 9. And then I'm just going to write down equation 1. I'm not changing it. I'll put it right here below. Okay? Now, if I did this correctly, I should have got rid of the z's. So this gives me a 5x. This gives me a 6y. The z's are gone, and then over here I get 7 for that guy. This is going to be equation 4, and this will be equation 5. Once again, that's just labeling. That's a reference to help me figure out what did I just do. All right. Well, can you see what I can figure out? I think I can get rid of y. If I multiply this by 6 and add it to this guy, the y's would cancel, right? I think that's what I'm going to do. Instead of me multiplying this by 2 and this by negative 5 and adding them to get rid of x's, I think I'm going to do the y's. Try to find the easiest route, okay? Not only does that mean less work, but that's less chance for you to make an error because, as you can see, there's a lot of steps here, all right? So I'm going to multiply equation 5 by 6, add it to equation 4. Okay, so let's do that. So let's see, this is going to be a 12x minus 6y equals negative 24, and this will be a 5x plus 6y equals 7. Okay, now if I did this correctly, the y should cancel. That's the goal, and I think I do. So this would be 17x, negative 6y plus 6y is 0. And you don't have to write 0, just you can leave it out of it. And then for this one, I get what, negative 17? So now I have an equation with one variable. To solve what's left, divide by 17, and I get negative 1 for that guy. Okay? Hooray, we got one variable. It's a lot of work for one variable. So these three planes intersect at the x-coordinate, negative 1. All right, well, let's substitute this now. I don't want to put it back in the original because, once again, I don't know what y and z are. That's not going to help me. So I'm going to plug it back into one of these two because all I have left is y to solve. And I'm going to sub it into equation 5. I think that one's a little bit simpler, okay? So I'm going to scroll that over, all right? And I'm going to substitute. So 2x minus y equals -4. So that's going to become 2 times -1 minus y equals -4 when I plug that number in. So that's a -2, which I have to add to this side. So I get -y equals -2. Divided by the negative, y becomes 2. Okay? All right, now, I want to make sure I can fit the whole thing in this screen. So now what I got to do is take both of these guys and plug it back into an original equation to find z. Okay? And it's always your choice. I think that's the beauty of these problems. There are so many ways of solving it. What you do might be different than the person next to you solving it. All right? But you should still come to the same answer if you algebraically did it correctly. I'm going to try equation 2 because that looks simple. Okay? So I'm going to sub x and y into equation 2. All right? So I get -1 plus 2 plus z equals -3 when I do that. So this becomes a +1, subtract it over, z comes out to be -4. All right, so then what I should do, goodbye, so long to those equations. Put this together, -1, 2, and -4. Boom. So this is the intersection point for all 3 planes. Okay? And that's it. So these 2 examples show you what is a normal expectation for this problem. You're trying to find answers to the system. That's behind me. Oh, right here. Which is a point, right? X, Y, and Z. So it's a 3-dimensional graph. All 3 planes are going to intersect at one point. So now for part 2 of the lesson, part 2 of the video, which I'll post later on, would be what happens when there's infinite solutions and no solutions. Visually, we can come up with what they look like, but how does it show up algebraically? All right, and that's what we're going to talk about in those parts. Okay, so have a good day, guys. I'll see you in the next lesson.